Good morning, students, physics students, one and all, to another episode of Finzics. It's Mr. Finn coming at you from neighborly Northville on a Friday. I hope you guys are doing great today. Don't forget, we've got a Google form today, our traditional Friday Google form coming out to help you guys with this week's material. We've got just one topic to discuss today, and that's the difference between alternating current and direct current. We talked about the current as the flow of charge per unit of time, or the amount of coulombs flowing through any area in any amount of time. So, in our labs, if we see these connectors between 2 points and a light bulb lit, that means there must be the flow of electric charge energy through that cord. Now, what is AC and DC? Well, simply they stand for direct current and alternating current. Direct current is easy enough to understand. That comes from a battery. So remember, we talked about the battery. It's just two different cells separated by a non-permeable membrane with some electrons, excess electrons, stored in one end and a deficit of electrons stored in the other end. A dry cell means it's some kind of ion, some powder of some kind, which will push electrons through the circuit. And of course, we know it's not the electrons themselves that move. They do move. It's the electron energy that we use. It's the collision energy that we use, which travels the speed of light. But any direct current will come from a battery of some kind, like this, or a voltage source that we establish at the beginning of the circuit that is fixed. Direct current, that means the same amount of current flows no matter what. Now, what is different from an alternating current? How does that differ? Let's have a little think about that. Since we don't have the fortunate experience of having electromagnetic induction in our back pocket, we're coming to that. We're going to have to just use a theoretical example. So I'm going to go to the board, but before I do, we know alternating current is stuff that you get when you plug into the wall. I plug my cord into the wall, alternating current. And basically, that means that we're getting a shift back and forth, a movement back and forth. So the electrons actually don't go anywhere. The power cycles back and forth. It's the energy that travels the speed of light. But electrons don't actually even migrate through an alternating current circuit. They simply just oscillate back and forth. So the electrons that you are using to light that light bulb actually come from the light bulb itself, if it's alternating current. They don't actually go anywhere. Now, why would they flip back and forth like that? Let's take a look on the board and see what happens. Okay, guys, what I've got here is just a little diagram. A turbine is what's used to produce AC current. Now, that turbine could come from a hydroelectric plant, a nuclear plant, a coal-burning plant, whatever kind of power plant you have. Somewhere we are using either gas or coal or running water or nuclear decay to make something turn around. A turbine somewhere in the plant is turning around. And by the magical process of electromagnetic induction, which we're talking about later, the turning of that turbine within a magnetic field produces electricity. This is the north pole, this is the south pole of a magnet, some kind of magnetic field. There are conductive pieces of magnets on the turbine itself. So when it turns around, when the magnets are high strength, they are applied to the north and south. And as it turns, a non-conductive piece turns into and turns off altogether. We're going to talk about that more when we get to electromagnetic induction. However, because of this omega, the spinning of this turbine in a 360-degree rotation, what we get for alternating current is a sinusoidal wave pattern. Down here, sinusoidal wave pattern. Looks just like what you'd see in math class. That's the production of our current, AC current. As opposed to DC, which simply puts out current in a straight line, continuously. So why does this matter? Well, it actually matters if we take a look at power. Power, you'll remember, was I squared times R. One of our another definitions of power, I squared times R. So if power is I squared times R, it doesn't matter if the current is negative, because power is not negative. So these negative values would be superimposed onto the positive part of the chart. But that means we wouldn't get the current at the top of the peak. We would get somewhat of an average, a cyclical current. So when you plug something into the wall, what you're getting is cyclical values. And that frequency is around 60 hertz, or about 120 changes every second if it's cyclical. So what value do we get by plugging into the wall? We don't get the peak, and we don't get the zero value either. It's somewhere in the middle. Let's take a look and see. Okay, guys, I've just made a couple of adjustments so you can see a little bit better. The average, doing some fancy mathematical manipulation, see Mr. Aziz or Mr. Avicic for more details, we get what's called a root mean square. This is the approximate average of the power that you would receive, or the current you would receive, by taking the middle of all these humps. It's not actually the middle. It's more like 70%. So if you had a peak value here, we're going to use that as I sub O. Through this fancy manipulation, we're going to come up with a root mean square value, which is about what you would get by plugging into the wall in terms of current. You might get a peak current, but if you divide that by root 2, which is about 1.41, we would get about 70% of the peak current as usable, dependable current. 70%. And the same root mean square value would go for voltage as well. Meaning a peak voltage would be divided by root 2, and it would give you about 0.707 of that peak voltage, or 70%. But where does the 70% come from? Guys, it just comes from the fact that we had to approximate. There's more of this value down here than it is up here. There's more time for the current to spend at these values, so the line is going to be a little bit skewed. But remember, these parts are flipped. So these lower parts of the current, where it goes negative, flips to a positive because power cannot be negative. So P equals I squared R. Now why is that? Well, that's just a circuit relationship. But we know the power is just as good if it's negative as if it's a positive. So it doesn't matter about the rotation of our turbine. It only matters that the power is going to be positive or usable power no matter what. And the dependable power we're going to get out of that wall is about 70% of the peak value that can be at any one time. That's very interesting. Well, let's see if we can wrap up this thing a little bit. Okay, guys, it's important to know the difference between AC and DC power. The AC comes from turbines, and it is cyclical because of the circular motion of the turbine. As far as values go, though, it's fairly simple to calculate your root mean square value by just taking 70% of the peak value, or having to calculate the peak value at any point in time by multiplying by 1.4 your root mean square value, or the root of 2 times the root mean square value would give you the peak value. So mathematically, it's pretty simple. But conceptually, maybe if we didn't understand about what actually happens to produce alternating current, it may have thrown you for a little bit of a loop. Now guys, where do we get alternating current? We get it from the household wall. Remember, somewhere on the other end of these local lines is a relay station where power lines come in. And then at the other end of that relay station, other side of those power lines coming in, all those lines have to lead back to some larger power plant that's actually producing or converting moving items into electric signal. So whether it's converting moving water to electric signal or converting nuclear decay and steam, we use those nuclear isotopes to create steam, and the steam goes through, turns the turbine. That's simply how a nuclear generator works. Okay, guys, don't forget your Friday Google form this week. As always, I don't really go, the Friday material doesn't show up necessarily very heavy on the Google form. There may be one question in general on it, but more of that will be included in next week's material because we don't have time to ask questions. Get to your Google Meets, guys, and make sure you're getting your homework done. And have a great weekend, and we'll see you next week.